everyone. My name is Angela Macedo Andrade, and I'll be your TA this summer term for Engineering 45. Today we're going to go over the Symmetry Lab. And for the Symmetry Lab, we're going to talk about translational symmetry, rotational symmetry, reflection symmetry, and do a few exercises, and then talk a little bit about the application in symmetry. So the first type of symmetry we're going to talk about is translational symmetry. And translational symmetry, you can think of a bit of the arrangement of atoms in a crystal, but it's basically when either an atom or an element or motif is has undergone some movement, and that movement either is a slide or a shift, and it has a specific direction and a specific distance. So you can think of it as moving an element along a vector with a magnitude and a direction, and it doesn't have any rotation or reflection. So if we think about this image here of the bird, or even you can think of it as atoms, you would get the same image or the same atom, the same motif, but repeated along a different direction or a different position, either in a 2D or a 3D space. In this case, we show this example of this motif of a bird being translated, being moved along a line and repeated. So we get the exact same image repeated along a different position. And so we see here that we have this repetition of images with the birds, and it's the exact same image, but just moved along a different direction and different lengths. And so, yeah, the same thing is here. It says the sentence has translation symmetry, which basically just shows you that it's the same image along some sort of length and direction. So rotational symmetry is different. It again, if you consider what we think of symmetry, which is having the exact same image, if we were to rotate this image along its center of rotation, or its center axis here, in order to get the exact same image, we would have to rotate it 360 degrees or not rotate it at all. And this type of rotational symmetry is known as one-fold rotation. And it basically implies that you either don't rotate or have to rotate 360 degrees in order to get the exact same image. And the same goes with this isosceles triangle here, where if we rotate about its center of rotation, we would have to rotate it 360 degrees in order to get the exact same image. Now, other types of rotational symmetry are twofold rotation, which would be shapes like a rectangle or sort of this elongated hexagonal, and it's often characterized by this oval shape and known as a dyad. So in a rectangle, in order to get the exact same image, if we rotate it about its central axis here, a central rotation, we would have to, in order to get the exact same image, we would have to rotate 180 degrees. And we can also rotate 360, which would just get us the same exact image too. But usually the twofold rotational operation moves an object by 180 degrees. And like I said earlier, that's usually identified, this type of rotational symmetry, which is twofold, is usually identified by this oval shape. And we also have threefold rotation, and a threefold rotation would be something like an equilateral triangle, which if we rotated about its center of rotation, in order to get the exact same image, we would have to rotate it about 120 degrees. And same goes with this sort of hexagonal shape, which I don't know the name of, but that has three things that are same and the other three things that are a little longer, and in order to get the exact same image, we would have to rotate 120 degrees. Or the smallest rotation that we can do would be of 120 degrees to get the exact same image. And so this is usually identified by this triangle and characterized and known as a triander. So fourfold rotational symmetry would be things like a square, or this shape here, where with the smallest amount of rotation that we would need in order to get this type, the exact same image, would be by 90 degrees. So if we were to rotate this square by its center of rotation, we would get the smallest rotation that we can do in order to get the exact same image, again, would be 90 degrees. And this is identified by this square or tetrad here. And then the sixfold rotation symmetry would be something like a hexagon. In a hexagon, the smallest angle would be 60 degrees, and the symbol used to designate sixfold axis would be a solid hexagon. And then we have pentradial rotational symmetry, which is usually some examples like this star here, which has these repetitive motifs every 72 degrees. In order to if we were to rotate this about its center axis in order to get the exact same image, we would have to rotate it with an about its center axis 72 degrees. In general, pentradial is packing is difficult, and it generates a lot of gaps if we were to use it or have that arrangement of atoms. So reflection symmetry now deals with mirror planes, and what that means is if these dashed planes represent mirror planes, and if an object like this square were to have, or it's shown here to have mirror symmetry, what it means is if I were to draw a plane here and identify its mirror plane, then if I were only to take this half, which is the left side of the square, and I put it against a mirror, I would complete the image and have a full square and also reflect the right side. So you can think of it as having the right hand side and the left hand side of an image to complete. So you can have this mirror plane here along the diagonal, and if I were to take this sort of what is now sort of like a triangle here and put it against a mirror, I would complete the square. And so that's indicative of having reflection symmetry, and the same goes here with the next image. So we have talked about translational symmetry, which can be considered the arrangement of atoms that are moved along different directions at different with different magnitude, and have sort of this arrangement of motifs or atoms. We also talked about rotational symmetry and the different types and how to identify. If we have sort of the twofold symmetry, we would use this oval shape. Threefold symmetry, we would use this triangle shape, and then the fourfold symmetry would use a square, and then the sixfold would use this hexagonal symbol. For mirror planes, so sort of to identify that there's reflection symmetry in an object or an element, we would basically draw the mirror plane, which sort of identifies that this element has a reflection symmetry where one side can complete the other to create the entire element or shape in this case. Okay, so now we talk about crystal structures, and in order to sort of characterize or identify different components of the crystal structure, we need to identify its unit cell, which can tell us a lot of the crystal structure without having to look at the entire lattice, because the unit cell can build the entire lattice. It's a repeated element. It's the smallest cell that reflects the symmetry of the structure. So not only is it a small unit, it's the smallest unit that can tell you everything about the symmetry of the structure. And if we know that this sort of unit is the same, but it's just repeated, then we don't have to look at the entire lattice, but just focus maybe on the unit cell. Now there's different types of unit cells. Primitive unit cells for some structures can tell you the symmetry of the structure, but often they just contain one lattice point, and they make up which are made up by the lattice points at each of the corners. That are made up from the lattice points at each of the corners. Now, primitive cells usually are the unit cell for simple cubic. But then when we go to the other types of crystal structures, we need to use non-primitive or conventional unit cells in order for us to reflect the symmetry of the entire structure or lattice. And non-primitive, or also known as conventional unit cells, contain additional lattice points. So not only one lattice point, but they can contain more than one, either at the face or within this unit cell. And obviously that would mean that they contain more than one lattice point. Now, a lattice point in a crystal is a point and a crystal has a specific arrangement of atoms, and it can be reproduced many times in a crystal. And then we'll see this more in some of the examples. And then lattice coordinates are given by specific positions of a point using a combination of lattice vectors. So this, we talked a little bit about that with the translational symmetry, where we get a motif, or you can think of it as an element or atom that has moved at a certain direction, certain magnitude. And so we can describe sort of the positions of different atoms in a lattice or a crystal structure by lattice coordinates or lattice vectors. So just a little bit more about primitive unit cells. So the conventional primitive unit cell has the shortest and most nearly equal lattice vectors bounding it. So I think in the book it defines a unit cell as a parallelepiped, or if you think of qubit structures, it can be a cube, but it would have basically an atom or potentially a lattice point at each of the corners, which would be 8 corners of a parallelepiped or cube. Conventional cells, they have more than one lattice point, like we said before. And the conventional cell is a cell that's obeying the following. It has the basis vectors defined at the right-handed axial settings. Its edges are along the symmetry directions of the lattice, and it's the smallest cell compatible with the above conditions. And then crystals having the same type of a conventional cell belong to the same crystal family. And I think the idea of primitive cells and conventional cells might make more sense here, where, for example, if you have a face-centered cubic structure, well, the FCC, the actual cube here that contains 8 atoms at each of the corners and then 6 atoms at the face center, would be your conventional unit cell, because it's basically is a motif that tells you about the symmetry of the entire lattice, and it's the smallest unit. Now, there could be a primitive unit cell inside the FCC, which is just like I said, it can be sort of this cube with atoms at each corner, which is the smallest motif, or the smallest units, or the atom arranged with the smallest distance. However, it doesn't really tell you the entire symmetry of an FCC. There are simple cubic structures which do have primitive cells to be their unit cells, because they're basically simple cubics. They don't have any atoms at the center, and that could tell you the entire, that type of unit cell, or this primitive unit cell, can tell you, describe the entire, or reflect the entire symmetry of the lattice. So yeah, so here, like we had the example here, primitive unit cells can be unit cells for simple cubics, because basically simple qubits have only atoms at each of the corners of the cube here. But other than simple cubics, for all the other types of crystal structures, you will have conventional unit cells which contain more than one lattice point. And basically this is an example of a BCC, right? That would be that its unit cell would basically be not only the atoms in each corner, but also account for the atom at the center, or the body centered. And so then that would make it have more than one lattice point. So for the first exercise, so here's some of the directions, and this is basically the same thing that I'm going to pin, very similar to what I'm going to pin for the discussion board. So we're going to look at identifying mesh or lattice points, unit meshes or unit cells, primitive unit cells, and conventional unit meshes. As you can see that even if you can identify a primitive cell in a certain pattern or lattice, but it might not be the unit cell of that lattice. So we'll look at it more in detail in when we're doing the exercises. But one thing to identify, you're going to hear a lot of mesh points, mesh, lattice, or lattice points. Mesh usually refers to 2D, while lattice is usually referring to 3D. And that's the same thing goes with the mesh points for 2D and then the lattice points for 3D. And then the second thing is we're going to learn to proper notation for representing mirror planes, or drawing the mirror planes, and rotation axis, drawing the different symbols, whether it be for threefold, the dyad, the tetrad, and so forth. And then basically show what rotational symmetry axis and mirror planes, and describing the repetitive patterns. And then develops, your spatial skills and thinking skills, and explore some connections between science and art. So I know we're seeing all these repetitive motifs, or basically images, but they can sort of give you an idea of how to perceive atoms in a crystal structure, which also have similar symmetry to these images that we're going to practice on, and also can identifying the symmetry in those patterns can also help us understand how to find the symmetry in crystal structures. So for some of these, we're going to select an arbitrary point, recognizable point, and we can identify that as our lattice point. Such points are termed mesh, lattice points, and a whole periodic array of the term are mesh, or the lattice. So you can think of it as you have one atom, and if you translate it or move it along some direction, or at some direction in length, then you can keep repeating sort of this array and have sort of the lattice or the mesh of different atoms, or in this case different motifs or different images on each of the patterns. Okay, so we're going to do we're going to identify a point, and we're going to identify it at the lattice point. In some of the exercises, we're going to try to find the unit cell, a primitive unit cell, find mirror planes, sort of identify its type of symmetry, if it has rotational symmetry, and so forth. So for this first image is by this Dutch artist, and it sort of looks like what are fishes, drawn in gray and red, and it's sort of this repetition of images or motifs, and we see that we have sort of some motifs of red fishes sort of touching each other's nose, and we also have these gray fishes touching at the, I guess, nose or mouth, whatever you like to call it, and sort of repeated throughout to form this pattern. Now, if we were to identify a lattice point, say at the center of the gray fish's snout, we say that this is our lattice point. Now, if we were to, I guess, identify the same image or the same lattice point throughout this pattern, we see that we have this sort of array or lattice of the same repeating motif or element. So we have these fishes touching our snout throughout the pattern in this arrangement. So we sort of see this array or lattice or mesh of gray fishes touching at the snout. Now, there are things that we can identify, right? So one of them would be identifying the primitive cell. So we have this sort of lattice point that we sort of identified and shown how it's distributed or moved or translated with translational symmetry along the pattern. We see that it sort of moved here, moved here, moved here, or we can think of it's moved to the left, to the right, and it's the same exact pattern translated differently throughout this pattern, or not translated different, but translated at different length and directions throughout this pattern. Now, we can identify its primitive cell to sort of being, if we were to translate this motif, if I were to pick this as my lattice point, it can be translated in this direction with this length, and in this direction with this length. And this length of the motif, or connecting these two, the same motifs, would be the shortest length. And having the shortest length between elements would be considered your primitive, would make up the primitive unit cell, which is this sort of what we would define as a unit cell with the short, not a unit cell, but a cell with the shortest distance of repeating motifs along a certain direction and length. Now we also identify of the primitive unit cell to having one lattice point, or in this case, if we're looking at 2D, one mesh point. So you can think of it, this is a parallelogram. The parallelogram would have what this would be 120 and 60 degrees and 60 degrees. So at 120, we have 1/3 of the mesh point. So we have two of them, so that would be 2/3. And then we have 60 degrees, which is 1/6 of the mesh point. So we have two 1/6, which make it 1/3. So this encompasses one mesh point. And so then that's one of the definitions for a unit cell, that it has to contain one lattice point, or in this case, one mesh point. But now that doesn't, identifying this unit cell doesn't reflect the entire symmetry of the pattern. And so then the smallest unit that we can identify the entire symmetry of the pattern would be this hexagonal, which contains sort of this center lattice point here. And this is the smallest arrangement of these elements that can tell us all, that can be repeated and can tell us the entire story about the symmetry of the pattern. And if we know we have a hexagonal, we know that we have a 6-fold rotational symmetry, and that is that if we were to rotate this image by 60 degrees, we would get the same image. So we're asked how many mesh points are there in each of the units meshes. So we identified sort of this to be the primitive unit cell, and like I said before to you guys, it has one mesh point, because if we were to consider, this would be basically 120 degrees, 100. So I think, like I said before, this would be one lattice point for the primitive unit cell, because it has two 1/3 and two 1/6, because it's 60 degrees of a point, which would be 1/6. So we have two of those that make 1/3, and that would make one mesh point. Now when we're looking at the unit cell, which tells us everything about the symmetry of this pattern, and it's the smallest unit that tells us everything about the symmetry of this pattern, we see that it is a hexagon, so it's 120. So it's 1/3, 1/3, and we have 6 1/3, or 6 corners of 120, which take up 1/3 of a lattice point, or in this point, sorry, a mesh point. So then that would give us two mesh points, and then the one in the center, which would give us a total of 3 mesh points. And we see here, you can also think about these 3 mesh points. You definitely want to consider the center and how they're translated to form the entire mesh unit, or unit mesh. And this would be considered your conventional unit mesh, and this would be considered your primitive unit mesh. Now, ways to identify symmetry in this case, here we can see that one of the rotational symmetries that we can identify is this 3-fold rotational symmetry, which is the snout of the fishes here. And we see that if we identify that type of symmetry with this sort of triangle, and we see that if we were to rotate this pattern or this motif by 120 degrees, we would get the exact same image. So we identify all the 3 folds rotational symmetries by these triangles. And the same can be done with this side, which is the basically the fins of these fishes, or the red fishes, where they meet. And if we were to rotate this motif 120, we would get also the same image. So we can sort of identify that rotational symmetry. And just symmetry, we can sort of, and the same 3-fold symmetry is for the snout of the fishes, red fishes touching, and we see that they also have a 3-fold rotational symmetry. And the same goes with the tails of the, we got the snout. Let's see, yeah. And so we fill this with the snout, or you can think of it fins of the gray fish. We try to encompass or account of all the symmetry throughout the pattern. And if we were to turn off the lights, we would see that we get this sort of arrangement or lattice of the repeating pattern or repeating motifs, which you can think of it as atoms, sort of the arrangement of atoms within a crystal structure and how they are sort of arranged. So the second would be sort of looking at this pattern or medieval pattern. We identify a lattice point here at the center. We see that we have this repeated lattice point or these points here. Now, in order to identify the primitive cell, like we said, we would try to see the shortest distance of the same motif or element translating in different directions throughout the pattern. And we see that this would be the smallest motif, which we would identify as the primitive cell. However, we see that this here has this sort of tetrad type of symmetry, which is, or fourfold type of symmetry, which is usually characterized by this square. And what that means is that if we were to rotate it every 90 degrees, we would get the exact same image. And so we see that this tetrad type of symmetry can be characterized by the squares, and that the dyad symmetry can be sort of identified, which dyad, as we recall, is if we were to rotate this image by 180 degrees, we would get the exact same image, and it's sort of identified by these oval shapes. Now, if we see this, we see that the arrangement of different types of symmetry looks something like this, with both the dyads and the tetrads making up an array of atoms. And now the third exercise, we see if we pick this as our lattice point, the center, and then pick this as our unit cell, which would say that as we repeat this sort of image, we would get, it would tell us everything about its symmetry of the pattern. And so then we identify the type of rotational symmetry by including these tetrads, or not tetrads, sorry, these squares, which are also, I guess, tetrads. And we see that has a 90-degree rotational symmetry. So we repeat it throughout. We see that there's some dyad symmetry also here. Now, we can also identify mirror planes here, as you can see here. So a mirror plane would be that if it has the same thing on one side, I mean not the same thing, but it has basically a reflection of the one side of the one side is reflected on the other side of the mirror plane. So you can think of it as, like I said before, if we were to cut this along the mirror plane that we identified here and put it against a mirror, we would get the image on the other side, or the right hand side image placed against the mirror would get us the left hand side. And so sort of the reflective or the reflection of one side of on one side of this plane would complete the image. And then I can identify that there's more than one mirror plane, sort of these diagonal. And then the n mirror planes intersecting at one point will give you an n-fold of axis symmetry, but not in any other, the other way around. So again, we sort of have this type of symmetry within this pattern. So we see that symmetry is everywhere. We see it in buildings and cities and in nature too. And diatoms are sort of, I guess, organisms that sort of build these structures. And they're very small, and they have sort of these repetitive and so we see that certain crystal structures for piezoelectric material which induce electric response depending on its structure. So there's an electrical response depending on the mechanical stresses, so they either cause an elongation or compression. Okay, so some of the applications would be piezoelectric material, which when a mechanical stress or a mechanical stress is applied, there can be some sort of electrical current. and this has to do with the rearrangement of dipole moments which occur when you apply this mechanical stress. Thank you for your attention, and I hope you guys have a good day.